I have already sent you the instruction sheets, lab instruction sheets, and today we'll talk about two experiments. One is pin-fin, the other is insulating powder. There are, so listen carefully, there are 5 to 6 experiments. There are 5 to 6 experiments, and each day we'll take 2. We'll discuss 2. So finally you have to prepare a lab report and submit. So hopefully if it opens, you can see the setup, but for the time being, you have to be satisfied with whatever we have. And also our presentation facility is not good. In fact, today, many of us are finding that recording option is also not allowed, because there is university has very less money. The financial situation is very bad, and we have very bad infrastructure. That is very unfortunate part, but we have to go with this. And the lab sheets are already mailed to you. In YouTube, you can also see the experiment if you like. The link has been given to you. So let us look at the heat transfer. So as you know, that heat transfer, there are 3 modes: conduction, convection. See, writing is also difficult. Online is very problematic. Radiation. So you know that Q is the heat transfer, and the unit of heat transfer, you can say joule. Joule is the heat transfer. So per unit time, if I talk of Q as heat transfer per unit time, this becomes joule per second. So what? So heat transfer rate is given by some wattage. So this is nothing but energy transfer rate. And you know from thermodynamics the difference between heat and work. So we'll not go into too much detail, but in conduction, you know that this is gradient driven. So Q is proportional to area. Q is proportional to delta T by delta X. So you write like this: Q is minus Ka dt dx. So a few questions here you must remember, that why a negative sign? Then what is the unit of K? These are some fundamental question you should be able to answer anytime if you are facing an interview and all, because these are very basic. And I also request you to go back to your heat transfer lessons, because you will have to recall that. We will not thoroughly cover that. So you have to go back to your heat transfer lesson, your notes or your book, and revisit the formulae. So can you tell me what is the unit of K? What is the unit of thermal conductivity? Shayak, can you tell us what is the unit of thermal conductivity?
So watts per meter Kelvin.
Okay. Yes.
Watts per meter Kelvin.
Watt per meter Kelvin. Very good. So you can derive that. And why there is a negative sign?
So because heat transferred from a higher temperature to lower temperature.
Very good. So that's okay. So these are very basic, but you must know these fundamentals, and you'll be using that. So conduction heat transfer. Next is, if you talk of convection, again this is called Newton's law of cooling. That there is a heat transfer coefficient H, there is a area, and there is some temperature difference, T minus T ref, some kind of temperature difference. Okay. So there is a need to go for dimensionless number. Dimensionless numbers are very much needed when you talk of fluid mechanics or heat transfer. For example, you know Reynolds number. Basically, Reynolds number is rho, some velocity, some characteristics length by viscosity. Okay. So these you know. For example, for a pipe flow, Reynolds number, we write like this: Reynolds number based on diameter. So this characteristics length is D, rho U average D by mu. Suppose we are talking of a plate. Plate has a length of L. So I can say Reynolds number based on length is rho U L by mu. So these characteristics length, this is defined by you. Okay. So, but you must maintain uniformity. But there is some freedom in defining this characteristics length. So for a circular thing, obviously the choice will be the diameter. So, and some kind of velocity. So for example, for a pipe flow, the average velocity is the characteristics velocity. So remember, it can be rho velocity D, rho velocity length, anything. So suppose you have a pipe. Suppose I have a pipe with this sort of cross section, triangular cross section. How can I calculate Reynolds number? Can you tell me? For example, let me ask Rahul. Rahul, can you tell me for a triangular pipe, how do I calculate Reynolds number?
Yes, sir. Sir, I think average length, sir. Average height, sir. I think characteristic length is average height.
Triangle. Sayap, what is your opinion? How do you calculate Reynolds number? For a triangular pipe or a elliptic pipe, cross section is elliptical. How do you calculate Reynolds number?
Sir, forgotten.
So actually we take the hydraulic diameter. So suppose this is the cross section, or this is the cross section, or say this is the cross section. A pipe can be like this also. Pipe is like this. So go for hydraulic diameter. So 4 into area by perimeter. So for a triangle, you know that area, perimeter is 3a, and area also you can calculate. So in fact, for a circle, what is the hydraulic diameter? 4 into pi by d square by 4 by pi d. So hydraulic diameter itself is d. For a say elliptic, 4 into area is ab, and perimeter is pi ab. And the perimeter, you have to calculate the perimeter. So based on this perimeter, you can find out the hydraulic diameter. So it can be based on hydraulic diameter, based on length and some kind of velocity. So why we do this? Say for example, you are talking of a 1-inch pipe. You are talking of a 1-inch pipe. You are talking of a 10-feet pipe. And you are talking of a 1 meter per second velocity. Or you may talk of 1 kilometer per second velocity. So how do I compare? Fluid mechanics is telling you compare in terms of Reynolds number. That means you don't have to compare diameter wise, but compare in terms of Reynolds number. So that means it is combining the velocity, the length scale, the viscosity, the density. So many parameters are combined together. Say for example, you are simulating a car. Suppose there is a car. A car is like this. So you want to find out its drag coefficient CD. So you have to test it in a wind tunnel. and Reynolds number is rho velocity of the car, that some dimension, some length of the height car by this thing. So you may not have the space to accommodate the car in the wind tunnel. So you take lower LC, but you change this, you make it higher LC. So you go for the same Reynolds number. So that is how it is easier to compare in terms of, say, in terms of Reynolds, some non-dimensional number. For example, the aspect ratio. It's like say, if you look at your face, your actual size may be like this. In a photograph, the size is like this. So you see the ratio of the eye to the whole thing here and here remains same. So that is like a dimensionless number, which is preserved. Similarly, you work for a particular Reynolds number means you are combining so many parameters. So that is Reynolds number. Similarly, for heat transfer coefficient, H, this H, what is the unit? First of all, this unit must be clear. So heat transfer is H A delta T. So unit of H is, this is watt per meter square because of this, and delta T, Kelvin. So unit of H is watt per meter square Kelvin. Now what is the dimensionless value of H? So let's say we have a flat plate. Now you see the wall is at TW. Suppose this is the wall at the room. Your room is at high temperature T. The room is at T infinity temperature and the wall is at TW temperature. So you can see the heat transfer is H into area into TW minus T infinity. But how heat transfer take place? On the wall, there is a boundary layer. So here only Ka dt dy on the wall is taking place. You just write down this. Follow me how I am doing. So Ha, if I look from convection, this is Ha TW minus TW, Q wall. And that is also conduction immediately at the wall, because on the wall there is no slip condition. So therefore on the wall this is the condition. So H TW minus T infinity is equal to Ka dt dy. Now if I think of non-dimensionalization, we can say that y star, non-dimensional y is y by L. And so A cancels. And how to do non-dimensional TW? We can say theta is equal to T minus T infinity by TW minus T infinity. This is how non-dimensional temperature. Can you tell me what is the value of theta on the wall? Suppose we non-dimensionalize this. Ritankar, can you tell me what is the non-dimensional value of theta on the wall? Or anybody?
Sir, 1.
1. Because on the wall, and what is the non-dimensional value on the free stream?
0, sir.
So see, this is the beauty of non-dimensionalization. Whatever is the temperature of the wall and whatever is the free stream, you are making it as 0 to 1 range. And so what is the value of theta star? What is the value of, so if you replace this, see H TW is how much? H TW minus T infinity is equal to minus K, and dt. You see that dt is equal to TW minus T infinity into d theta. If you look this equation, this is constant, this is constant, this is constant. Only this is a variable, this is a variable. So dt is d theta into TW minus T infinity. So H TW minus T infinity is equal to minus K. dt is how much? TW minus T infinity d theta And dy is how much? Y star is y by L. So dy is equal to L dy star. L dy star. So what is this? How now you can see what is d theta dy. So these equations give me d theta dy is equal to HL by K. So d theta by dy star is equal to minus HL by K is equal to minus what we call is Nusselt number. So you see that HL by K is the non-dimensional number, which is known as Nusselt number, NU. In the name of a scientist Nusselt, this is Nusselt number HL by K. So this is nothing but non-dimensional temperature gradient on the wall. So Nusselt number is giving me an estimate of heat transfer coefficient. So basically Nusselt number is nothing but heat transfer coefficient, but it is non-dimensionalized with respect to L and K. So L is D for circular thing, L is hydraulic diameter, L can be length. So some kind of characteristics length. So HL by K is the Nusselt number. Is it clear?
Yes, sir.
Okay, that's right. Now let me talk of more convection. Convection can be forced and natural. So you know that when there is something, some agency, a pump, a compressor, a blower is forcing the thing, then this is forced convection. Otherwise, if there is, this is due to density difference or concentration difference or say some other kind of agency, then it is natural convection. So what is the driving force for weather pattern? We are talking of weather prediction. So weather prediction is nothing but solving the natural convection equation, because there is a temperature difference, density difference in the atmosphere. So not only air, in the oceanic circulation also. You have heard of El Nino. So there is ocean temperature in the ocean, temperature in the atmosphere, radiation is coming. So finally it is a problem of natural convection. So, and if you solve this problem, you can predict tomorrow's weather. So actually, mechanical engineers are also in such professions. One of my students is in Pune National Meteorological Laboratory. So in the weather prediction team, they are developing code for weather, and you see that they are improving also, because there is a complex problem. Over the years, they are developing things so that from today's data of ocean temperature, the local temperature, air flow rate, you can predict what is going to happen tomorrow. So this is the biggest problem, is natural convection. In the atmosphere, what we find, that is the natural convection. But anyway, without going into detail, forced convection and natural convection. So now what is the typical magnitude? H. So heat transfer coefficient for natural convection may be 5 to 10 watt. This is a typical value, 5 to 10 watt per meter square. Suppose you want to cool your tea. You have a plate. You are pouring your tea on the plate. So typically 1 meter square surface area, 5 watt of temperature will be transferred per unit temperature difference. So this is natural convection. But if you move from natural to force, H will be high. H will be high when you go for forced convection. So in forced convection, you get more H. So you know that you have let's say two-wheeler engine. Let's say this is the two-wheeler IC engine. So there is this thing, but there is heat. So the two-wheeler, if you talk of two-wheeler, it is air cooled. But if you talk of a four-wheeler, is the engine air cooled? Can you tell me, is the engine of a four-wheeler air cooled? Yes
No,
or no?
sir. Fluid.
No, sir. Fluid.
No, because you need, so that means air gives you less heat transfer. If you go to water, it will give you more heat transfer. So if you remember your lessons in heat transfer coefficient, you'll find that Nusselt number is a function of Reynolds number and Prandtl number. So that means if you want to increase Reynolds number, you should increase, Nusselt number hit. That means if you want to increase heat transfer, you must increase your Reynolds number and Prandtl number. So how to increase Reynolds number? Basically rho V d by mu. So this is the object. So engine size you cannot change. Density you can change, viscosity you can change by cooling fluid, or you can change the velocity. So if you put more velocity, like if you want to cool your plate, you put more fan. The fan you run at high velocity, there will be more heat transfer. Similarly, what is Prandtl number? So Cp mu by K. Also, this is given by nu by K. So that means kinematic viscosity by, thermal diffusivity. So this is also a dimensionless number. Do you remember what is the unit of thermal diffusivity? Can you tell me? Or kinematic viscosity, what is the unit? Both have the same unit, so that Prandtl number is non-dimensional number. So what is the unit?
Meter square per second.
Very good, meter square per second. Why meter square per second? Diffusion things are having a dimension of meter square per second. Suppose there is a drop of ink. What will happen? This ink will spread in the water. Okay. Suppose this room is filled with water, you put a drop of ink. Now this area of influence will grow, or there is some chemical released. So the chemical will go on increasing the area. So this is the area increase per unit time. That is why the diffusion gives a unit like this. That means it is going on creating a area of influence. The sphere is increasing in area. Anyway, so and also Prandtl number, some other important thing you should keep in mind. Like Prandtl number is, you know that delta T, thermal boundary layer, and say hydrodynamic boundary layer. So you may remember that hydrodynamic boundary layer by thermal boundary layer is related to 1 by PR. Go back to your heat transfer relation. See, PR is greater than 1, then thermal boundary layer is high, and PR is less than 1, then hydrodynamic boundary layer is means over this. Okay, which one is higher height? That you can find out from this relationship. Delta by delta T is related to 1 by PR. Sometimes there is a PR to the power n. So you have to have an idea of what is the order of PR. PR is about 1 for which fluid? Air. PR less than 1. Can you tell me when PR is much less than 1? Do you know? Liquid metal. For liquid metal, and liquid metal is very important, like casting industry. If you visit steel plant, you will see there is a river of liquid metal. So you have to think about that. And PR is greater than 1 for say mineral oil, say water. So remember this. Okay. So this is something you have to know. So you can see that if you change the PR, the fluid will, there will be more heat transfer. So you go for car, you go for water cooling, that means you are changing PR. So that means how heat transfer coefficient change? If you go from forced natural to forced, heat transfer will change. If you change the fluid from gas to liquid, it will change. And when you get maximum heat transfer, when you do what is called phase change. When you do what phase change. then you get maximum heat transfer. Can you tell me an example of phase change, liquid to vapor?
Yes, sir.
Can you tell? Like your refrigerator, there is a working fluid. How it transfer heat? The heat is transferred by freon or some this fluid, working fluid in the refrigeration circuit. It takes up the heat and moves. Or steam in a power plant, that also takes up the heat. And for very high transfer, it should take the latent heat HFG. So there is phase change is also involved. So what we are learning, that heat transfer increases if you move from natural to forced, gas to liquid, and go to phase change. So maximum heat transfer you go for when you do phase change. Have you heard of the term heat pipe? In this context, let me talk of something known as heat pipe. Do you know what is a heat pipe?
No, sir.
No, sir.
Okay. So this is what is in Hindi it is called diya. Bangla amra boli sholte. Okay, Pradeep sholte, you know diya.
Yes, sir.
Yes,
So
sir.
why it is not burning?
Yes, sir.
This is made of fiber, but it is not burning. Why? Because it pumps oil, isn't it? So as long as there is oil, it is pumping the oil through the. Actually, it is a porous structure because it is cotton. There is pore. There is pore. There is porous structure. So it pumps the oil due to capillary action. So there is oil. It is pumping up the oil to the end, and this is supporting the flame. So as long as it goes on pumping, it will not destruct it. But when the oil reduces, this diya will also burn. So this porous action, if you have something like this, you know, you have studied the refrigerator circuit, you know, evaporator condenser.
Yes, sir. Yes.
Yes, sir.
So suppose here this is the evaporator side. Okay. So you have something here, heat is coming. So there is a fluid which evaporates and goes like to the other end. Then it condenses. Now it has become liquid because it gives the heat transfer. Now there is a porous structure. This part is made of pore. This part is made of pore. So some alcohol-like fluid is here. It will evaporate, go to the other end, release the heat, then it will become liquid, and there is a pore. There is like diya. Okay. So there is like ceramic, this candle in filter you have seen. So it will come through this. So this way, it is like a complete condenser evaporator circuit, but in a one piece. So it is called a heat pipe. Actually, in your laptop, flat heat pipe is there. Heat pipe you can find in laptop. It can be very large. LED light in high-end car. So this LED light must be cooled. So there is a heat pipe. And it can be made flat like this. It can be like this. So very complex path it can take. So heat will go, and through the diya it will come back again. The fluid will circulate from one end to other end. Anyway, these are all advanced things. But now today's experiment, we want to find out heat transfer from a pin fin. Okay. So you have already have this note. I mean, this lab sheet. Okay. So here, this is here there is a fin. Okay, pin fin. That means it's like a straight line. So one end is hot, the other end is cold, and air is going through this. So you have to find out. Let me actually write it in the board. This pin becoming difficult. So you have solved the pin fin distribution. I will not discuss it again because it has been already covered in your heat transfer note. So this side there is temperature 1, this side temperature 2. So you measure the temperature distribution 1, 2, 3, 4. So these are the measured value of temperature along the fin. So this is a fin and you measure the temperature T along X. Now you know a theoretical distribution also. You know that the theoretical distribution is given in the lab sheet or in your note. That the theoretical distribution is coming from this equation, del square theta del x square minus m square theta. So del square theta del x square minus m square theta is equal to 0. This is the equation for pin heat transfer. So from these, you can find out the theoretical point. So these are the experiment point, and let's say these are the theoretical. So this theory you have to calculate, and experiment you have to measure. Now, then you have to calculate fin efficiency and fin effectiveness. You see that the equation for heat transfer is HA delta T. So if you provide more area, then Q increases. So fin is nothing but providing more area. Like in this context, why do elephants have big ears? You have seen elephant and they have big ears. So what is the reason?
Big heat transfer.
More area.
So more area. Actually, in human being, there is a mechanism known as thermoregulation. So if you are when it's winter, you will be shivering. That means if your temperature is not being controlled to the core temperature, shivering means that is work to heat transfer. So by shivering, it produces heat. And in summer, sweating. So sweating means there will be evaporation, and that will also reduce the temperature. But elephants, they don't have that mechanism. So nature has given them high area. So if you look at the ear of the elephant, you will see there are veins. There are arteries and veins. So they are through this the blood is going, and now it is exchanging heat. So it cannot control H. It cannot control delta T, because the ambient is in the reach of the elephant. It cannot control ambient temperature, but nature has given him high A. So increasing area. For example, it is a cylinder. Now you can put a ring like this. These rings are circular fin. So they are giving extra area. So this fin efficiency and fin effectiveness, what is that? Suppose this is the original surface and this is the extra area. So this is the base temperature. Now everywhere if it is the base temperature, then it will have the Q ideal. But actually there is a distribution like this. So that is the Q actual. So Q actual by Q ideal, that is giving you fin efficiency. So what can be the maximum fin efficiency? What is the value it can approach?
HA TB minus.
No, that means when everywhere it is TB, that is the ideal, and other it is not really ideal, there is a distribution. So it must be less than 1. But fin effectiveness must be greater than 1, because you are putting a lot of area. So fin effectiveness can be 30, 40, 50. But efficiency means it's actual how much heat transfer it is doing. And had it been everywhere at the same base temperature, had it been flat like this, then what is the heat transfer? So that situation is known as Q ideal. So fin efficiency is always within 1, and fin effectiveness must be large, 20, 30, 40. So this you remember. So in this lab sheet, what you will see that there is a setup. Okay, there is a setup where there is a fin. So the fin is like this. Fin is going like this, and 1, 2, 3, 4, 5. At the 5 point, we are measuring temperature. You see measurement of temperature. First point 77, second point 73, third point 69, and ambient temperature. So now you can plot that. You can plot the temperature along this line, theoretical and actual. So theoretically you will calculate from this formula, del square theta del x square minus, so you have, it has a distribution, this is derived here. So t minus tf by t1 minus tf is cos h m l minus x, like this. And you see that this is an important formula. M is hp by ka. So these also you have done already in your, this is hp by ka in your heat transfer class, so I'll not go into that. But what is your task? Your task is to use this data, calculate the theoretical distribution, plot the theoretical distribution, and plot the actual distribution. Then write why there is difference, why there is deviation, and also show the sample calculation. Now you see, this is the setup. What is happening? This is the fin is here and air is going through this. Okay. And here there is a manometer. What does the manometer do? It measures the pressure difference. So from this pressure difference, we calculate the velocity. So why we need the velocity? Because we need the value of heat transfer coefficient. Okay. We need the value of heat transfer coefficient H. So heat transfer coefficient, again I am writing this just to need a fresh pen. So I need to theoretically calculate the distribution of temperature here. So I need to calculate M, which is root over Hp by Ka. So I need the value of heat transfer coefficient. Okay. So this heat transfer coefficient is calculated from a correlation. So function of Reynolds number and Prandtl number. So in this work, it is a function of Reynolds number. So if I know this function, I can calculate nu is equal to HL by K. So L is the diameter of the fin, and thermal conductivity you can find out, so you can calculate H. So this is the function, Nusselt number, how it is Reynolds number dependent. You see, this is the function. Nu is 0.615 RE, and this is like this. So you have to use this. So one can ask you that why we calculate Reynolds number at all? It is a thermal conductivity experiment. Because if I want to find out the heat transfer here, I need to know what is the value of H, heat transfer coefficient. And heat transfer coefficient is obtained from this correlation. This correlation, Nusselt number is 0.615, Reynolds number to the power this. So let me tell a few words about the correlation. So correlation is not a mathematically derived formula, but this is some working relationship. For example, say if you find out that rain and say paddy price. So maybe if it is too low rain, paddy price is high, and at a moderate rain, the paddy price is proper. Then high rain is again paddy price is going. So you can find out an equation. So these equation is not mathematically derived, but observing something, you form an equation. Similarly, Nusselt number and RE, somebody has observed and come up an equation. Say for example, this is a correlation known as Dittus-Boelter correlation, 0.8, Prandtl number to the power 0.4. So that means you have to calculate Reynolds number, you have to calculate Prandtl number, and then you can find out Nusselt number. So it is not mathematically derived, but experimentally a relationship has been established. So something about correlation is how to calculate Reynolds number. So rho, the velocity you can calculate, diameter is known, but what about this rho and viscosity? You know that they are temperature dependent. So the rule is evaluate property, evaluate physical property at mean temperature. For example, the pipe is at 40 degree and fluid is coming at 20 degree. Take density and viscosity as 30 degree. But suppose something is written like mu s, that means mu at surface temperature. Then you take at the surface temperature only. But otherwise, you take the value only at mean temperature. Is it clear?
Sir,
Yes, sir.
question ছিল।
Yes, sir.
So, these are clearly written and you can see the video. Then what is your task? Calculate the theoretical. So listen to me carefully. What you have to do, calculate plot the theoretical temperature distribution along with experimental points two is why. Explain theory and explain will not match 100%, so you have to explain why. You have to search yourself. I will not explain because, for example, there is uncertainty in the experiment, the instrument may have some error, then we have some assumption. Explain why there is a difference between experiment and theory. Then next week no class, but by 4th okay. So you can use computer, you can use Excel plot to plot things, but in the same page the experimental and theoretical must be there. As I told you that it will look like this. Let's say this is the experimental point 1 2 3 4 and theoretical may be like this. So this must be in the same plot. Okay. And then why the deviation? The deviation must be explained to you, and results, the calculation. So you write in your own format. First experiment, let me see how you are individually doing, and submit to the mail address I'll give you by email. I'll send you further instruction. So that is all for today. Look at the experiment done in the YouTube video, and also look at the calculation sheet provided. Yes, please tell me.
হ্যাঁ স্যার, বলছিলাম যে আমরা যে পিনফিনের ক্যালকুলেশনটা করি ওটাতে তো আমরা মানে অ্যাম্বিয়েন্টটাকে তো জিরো ভেলোসিটিতে ধরে করি, মানে ওই হিট ট্রান্সফারটা তো মানে কোনো মানে এমনি ন্যাচারাল কনভেকশন, কিন্তু এইখানে তো ব্লোয়ার দিয়ে ব্লো করে তারপরে ওই এইচটা বার করছি, তাহলে একটা মানে ফ্লাকচুয়েশন আসবে না?
না না, ওটা তো ডেরিভেশন তো করাই আছে, এইচ এর ভ্যালু তো আছে। তুমি ইফ ইউ লুক এট দ্য ইকুয়েশন del square theta del x square minus m square theta, where m is including h, so that is why we require h, heat transfer coefficient.
আচ্ছা, এইচটা কেন বুঝতে পারছি, মানে ওইটা এমনি পিনফিনের যে নরমাল যখন ডিরাইভ করি ইকুয়েশন গভর্নিং এটা মানে ডিফারেন্সিয়াল ইকুয়েশন ডিরাইভ করি তখন তো মানে কোনো মানে ভেলোসিটি ধরি না।
কে বলছো ধরো না? এইচ ধরো মানেই তো ভেলোসিটি ধরো। এইচটা কোথা থেকে আসছে? আমি যদি ভেলোসিটি না ধরি ফ্রি কনভেকশন এইচটা কিরকম হবে? বাট এইচ ইজ, you see, this looks like this. It is a piece. This side it is T, this side it is T plus delta T, and here heat is going like H into T minus T infinity. This way it has been done. So this is H, Now h, if it is forced, then h you have to use, will have one set of value. If it is natural convection, you can take somewhat near 0, or you can put, but the expression, final expression is del square theta del x square minus m square theta, where m is h p by k as far as I remember. So h p by k, here h is included, so therefore you need to calculate h. You look at the expression, you have forgotten h is taken.
না ওই এইচটা যে ভেলোসিটিটা তোলে ওইটা ভুলে গেছে, মানে এইচটা মনে ছিল আমার। আমি ভাবছিলাম, মানে ভেবেছিলাম আর কি এইচটা আর কি পুরো শুধু নর্মাল সিচুয়েশনের জন্য।
H can be forced on natural, then h will have low value, m will have low value. Then if h is
ওই এইচ এর মধ্যে পুরো সিচুয়েশনটা আছে আর কি।
yes, it is included in that equation. It is already there in any book, and also this lab sheet. There may be some error of this there, but more or less the procedure is this thing. Okay.
Okay, sir. Thank you.
Okay. So next week there is no class, and submit the first set of report by 4th. Okay.
বেরিয়ে গেছে স্যার।
এ ভাই বলছি ডেটা কোথা থেকে তুলবো? ল্যাব শিটটা থেকে